We stand at a precipice, a species born of stardust, cradled on a singular pale blue sphere, yet possessed by an insatiable yearning to touch the very stars from which we came. It is a dream woven into the fabric of our consciousness, a whisper from the cosmos that beckons us outward, beyond the familiar comforts of our terrestrial home. But this dream, so luminous and compelling, collides with a reality far starker, far more unforgiving than our mythologies often portray. The universe, in its silent, sprawling majesty, is not a garden awaiting our arrival, nor a canvas eager for our imprint. It is an arena of profound contradictions, a realm where the very laws that govern its existence seem engineered for the extinction of fragile, water-based life such as ours. This is the story of that contradiction, of our audacious ambition to transcend our earthly origins, and of the immense, perhaps impossible, challenges that lie in wait. It is a journey into the heart of what it means to be human when faced with the ultimate frontier, a frontier that questions not only our capabilities, but the very essence of our being. We look up at the night sky, a tapestry of distant suns, and feel a pull, an ancient echo of our cosmic lineage. But what awaits us in that vast, indifferent expanse? Is it destiny, or is it a beautiful, perilous illusion? The quest to live beyond Earth forces us to confront these questions, to stare into the abyss and ponder our place within an existence far grander and more terrifying than we can easily comprehend. The story begins not with triumph, but with a fundamental truth: space is trying to kill you. The cosmic hostility and our earthly cradle. Space, in its stark and unyielding reality, is not the welcoming frontier of our most cherished fictions, but an environment intrinsically, almost deliberately, designed for our demise. This is not a turn of phrase meant for dramatic impact. It is a cold, hard assessment of the physical laws that govern the vast emptiness beyond our world. Consider the very notion of emptiness itself. The vacuum of space is so profound that it challenges our most basic sensory experiences. Here, sound, the medium of our voices, our music, the rustling of leaves, the crash of waves, simply cannot travel. The universe, from its very inception, established silence as its natural, dominant state, the cacophony of life, the symphony of a living planet. These are cosmic anomalies, fleeting whispers in an eternity of quietude. To step outside Earth's thin, precious atmospheric bubble is to enter a realm where your own heartbeat, the rush of air in your lungs, the words you might cry out, would be swallowed by an absolute stillness, a silence so complete it borders on the terrifying. This initial confrontation with the nature of space is but a prelude to the myriad ways the cosmos is engineered against us. Our planet, Earth, is a masterpiece of precise calibration, a sanctuary meticulously sculpted over 4.5 billion years to nurture the emergence and evolution of complex life. Every facet of our existence, every fiber of our being, is attuned to its specific conditions. Think of gravity, that constant, gentle pull that has shaped our skeletons, dictated the strength of our muscles, and engineered the intricate pathways of our circulatory systems, ensuring blood reaches our brains against its relentless tug. Our bones have developed a specific density to support our weight in this particular gravitational field. Our muscles have achieved a balance, strong enough for movement, but not so overdeveloped as to be inefficient. Then there is our atmosphere, not just a breathable mix of gases, but a crucial pressure vessel. This atmospheric pressure, something we rarely consciously perceive, is vital. It prevents the fluids in our bodies, our very blood, from boiling away at normal body temperatures. It acts as a shield, a multi-layered defense against the harshness of space. It burns up most of the meteoroids that would otherwise pummel our surface, and it filters out some of the sun's more harmful radiation. The exact composition of this air, roughly 78% nitrogen, 21% oxygen, and trace amounts of other gases, is no accident. It is the product of eons of biological activity, a life support system created by life itself. Beyond the atmosphere lies Earth's magnetic field, an invisible guardian generated by the churning of molten iron in our planet's core. This magnetosphere deflects the solar wind, a constant stream of charged particles flowing from the sun, and shields us from a significant portion of cosmic radiation. Those high-energy particles originating from distant supernovae and other violent cosmic events. Without this magnetic shield, the solar wind would gradually strip away our atmosphere, as it likely did to Mars, leaving the surface exposed and sterile. And consider our distance from the sun, the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on the surface. Liquid water, the solvent of life as we know it, the medium in which the complex chemistry of biology unfolds. This precise orbital placement is a cornerstone of our habitability. Our entire biological architecture, from the macroscopic design of our organ systems down to the microscopic machinery within our cells, is calibrated to function optimally within this one specific, extraordinarily rare environment. We are, in every conceivable way, creatures of Earth. So, what happens when this perfectly tuned organism is removed from its bespoke habitat and thrust into the alien conditions of space? The answer is swift and brutal. The body begins to betray its terrestrial heritage. In the microgravity environment of orbit, or the complete absence of gravity in deep space, the signals that have guided our physiological development for millions of years are suddenly absent or distorted. Bones, no longer needing to support weight against Earth's pull, begin to leach calcium. This demineralization occurs at an alarming rate. Roughly 1 to 2% of bone mass lost per month, a rate comparable to advanced osteoporosis in the elderly on Earth. Over extended periods, this leads to a significant weakening of the skeletal structure, increasing the risk of fractures upon return to a gravity environment or even during activities in space. Muscles must, too, begin to atrophy. Without the constant resistance of gravity, they lose mass and strength. This includes the heart, a muscle that has evolved to pump blood upwards to the brain against Earth's pull. In space, this task becomes easier, and like any underused muscle, the heart can begin to weaken and even change shape, potentially leading to cardiovascular problems. Fluids within the body, no longer pulled downwards by gravity, redistribute upwards, leading to a puffy face, sinus congestion, and a sensation often described as having a constant head cold. More troublingly, this fluid shift can increase intracranial pressure and put pressure on the optic nerve, leading to changes in vision, a condition known as spaceflight-associated neuroocular syndrome, or SANS, which has affected a significant number of astronauts on long-duration missions. The spine elongates as the vertebrae decompress without the constant compressive force of gravity, sometimes causing back pain and nerve issues. The delicate balance of the inner ear, which relies on gravity to orient us, becomes confused, leading to space adaptation syndrome, a form of motion sickness characterized by nausea and disorientation, affecting many astronauts during their initial days in orbit. And then there is the silent, invisible threat of cosmic radiation. Unfiltered by Earth's atmosphere and magnetic field, high-energy particles, protons, helium nuclei, and heavier ions called HZE particles stream through space, capable of penetrating spacecraft and human tissue. These particles can damage DNA within our cells, increasing the long-term risk of cancer. They can also affect the central nervous system, potentially leading to cognitive decline, memory impairment, and an increased risk of neurodegenerative diseases later in life. Our very cells seem to recognize the alien nature of space, initiating stress responses and altering gene expression in ways that suggest a fundamental incompatibility. The irony is profound. The universe that birthed the elements within us, that set the stage for our solar system's formation and the eventual emergence of life on Earth, is simultaneously an environment profoundly hostile to our continued existence beyond our planetary womb. Every system in our body, finely tuned over countless generations to the rhythms and pressures of Earth, finds itself adrift, struggling to cope with conditions for which it has no evolutionary precedent. This immediate biological rebellion is not merely an inconvenience to be overcome with clever engineering. It is a fundamental statement from our own physiology. It whispers and sometimes screams, a disquieting question if our bodies so violently reject the cosmos. Were we ever truly meant to live there at all? Earth, our cradle, meticulously prepared itself over geological eons, through volcanic upheavals, asteroid bombardments, atmospheric transformations, and the slow, patient dance of plate tectonics. It was a process of almost unimaginable duration and complexity, culminating in a world uniquely suited to us. Space, by stark contrast, offers only an immediate and lethal contradiction to our evolved nature, a constant reminder that we are at our core children of Earth, intricately and perhaps irrevocably bound to our home. The impossible dream of new Earths. The dream of establishing humanity among the stars, of transforming alien landscapes like Mars into verdant, habitable new Earths is a potent and enduring vision. It speaks to our exploratory spirit, our resilience, our innate desire to expand our horizons. Yet, this vision of rapid colonization, of achieving in mere decades or centuries what nature took billions of years to accomplish on Earth, collides forcefully with the harsh realities of planetary science and cosmic physics. Our own planet's journey to habitability was a saga of immense timescale and improbable fortune. 4.5 billion years of relentless geological and atmospheric transformation, of volcanic eruptions spewing gases that would form early atmospheres, of cataclysmic asteroid impacts delivering water and organic compounds, of the slow, grinding dance of plate tectonics recycling crust and regulating climate, and crucially, of the emergence of life itself, which gradually, painstakingly, transformed a poisonous early atmosphere into the oxygen-rich air we breathe today. This was not intelligent design in the conventional sense, but a breathtakingly complex interplay of chance and necessity, an incomprehensible stroke of luck played out over deep geological time. To imagine we can replicate this miracle on a world like Mars within the span of a few human generations is to underestimate the profound challenges involved. Mars, the red planet, is not a blank canvas patiently awaiting human artistry. It is a world that actively resists habitation. Its current state is a cautionary tale of planetary evolution. Once, perhaps, a warmer, wetter world with a thicker atmosphere and a protective magnetic field, Mars lost these life-sustaining attributes. Its smaller size allowed its internal heat to dissipate more quickly than Earth's, causing its core to cool and solidify. This led to the demise of its global magnetic field, leaving its atmosphere vulnerable to being stripped away by the relentless solar wind over billions of years. What remains is a thin, tenuous shroud, less than 1% the pressure of Earth's atmosphere, offering little protection from solar and cosmic radiation and incapable of trapping enough heat to keep the surface from freezing. The Martian surface is a desolate, cold desert, Its average temperature hovers around a frigid -80 degrees Fahrenheit, though it can plummet to -225 degrees in winter at the poles. Its atmosphere is predominantly carbon dioxide, unbreathable to humans. Its water, while present, is largely locked up as ice in the polar caps and underground permafrost, or has escaped into space. The soil, or regolith, is permeated with toxic perchlorates, chemicals that would need to be removed or neutralized before any large-scale agriculture could be attempted. And then there are the dust storms, colossal events that can engulf the entire planet for months, choking solar panels, abrading equipment, and posing a severe hazard to any surface operations. Every single day on Mars, for every human inhabitant, would necessitate a continuous, complex, and failure-intolerant technological intervention just to maintain the basic necessities of life: breathable air, liquid water, adequate warmth, and protection from radiation. If one could somehow stand on the Martian surface without a spacesuit, the experience would be horrifyingly brief. The low atmospheric pressure would cause the fluids in your body, the moisture on your tongue, in your eyes, in your lungs, and even your blood itself, to begin to boil at body temperatures in about 90 seconds. Your final conscious moments would be an excruciating agony as your body literally vaporized from the inside out. The universe's verdict on unprotected human life on Mars would be swift, unequivocal, and brutal. You do not belong here. Beyond the specific challenges of Mars, the very act of journeying into space is a testament to cosmic tyranny, a battle against fundamental physics. To escape Earth's substantial gravity requires accelerating a spacecraft to a velocity of approximately 11.2 kilometers per second, or about 25,000 miles per hour. The energy required to achieve this is immense. Consider the Saturn V rocket, the marvel of engineering that carried humans to the moon. It stood 363 feet tall and weighed 6.2 million pounds at liftoff. The vast majority of this mass was fuel, expended with ferocious intensity in mere minutes, all to deliver a tiny lunar module weighing just 32,399 pounds to the moon, along with the command and service module. The inefficiency is staggering, akin to building an entire ocean liner to transport a single small suitcase across the Atlantic. And this monumental effort was merely to reach our closest celestial neighbor. The distances beyond the moon become nearly incomprehensible, stretching the limits of our intuition. Mars, at its closest orbital approach to Earth, still lies an average of about 34 million miles away, though this can extend to over 250 million miles depending on orbital positions. Even with our most advanced current propulsion technologies, a one-way journey to Mars takes 6 to 9 months. During this transit, astronauts are confined to relatively small spacecraft, exposed to cosmic radiation and living in microgravity with all its attendant physiological challenges. Now consider the stars, the nearest star system to our Sun. Alpha Centauri is approximately 4.37 light-years distant. A light-year, the distance light travels in 1 year, is about 5.88 trillion miles. So, Alpha Centauri is over 25 trillion miles away. Our fastest outbound spacecraft, such as the Voyager probes, are traveling at speeds that, while impressive by terrestrial standards, are utterly dwarfed by interstellar distances. It would take Voyager 1 approximately 73,000 years to reach the vicinity of Alpha Centauri, assuming it were even heading in that direction, which it is not. 73,000 years, multiple generations, thousands of them, would live and die in transit, never knowing Earth, their planet of origin, nor their final destination, existing solely as links in a vast, unimaginably long chain of cosmic migration. The psychological and societal implications of such multi-generational voyages are profound and largely unexplored. This tyranny of distance and energy is mathematically enshrined in the Tsiolkovsky rocket equation, a fundamental principle of astronautics. It dictates that the change in velocity a rocket can achieve is directly proportional to its exhaust velocity and the natural logarithm of the ratio of its initial mass to its final mass. In simpler terms, to go faster or to carry more payload, you need exponentially more fuel. But more fuel means more mass, which in turn requires even more fuel to accelerate at that additional mass. This creates a vicious cycle, a mathematical reality that severely constrains our cosmic ambitions with current chemical rocket technology. It means that building spacecraft capable of rapid interstellar travel, or even rapid interplanetary travel with substantial payloads, faces enormous, perhaps insurmountable, hurdles with conventional propulsion. Thus, the dream of creating new Earths, of seeding humanity across the cosmos, is not merely an engineering challenge waiting to be solved with sufficient ingenuity and willpower. It is a confrontation with the fundamental scale of the universe, with the immutable laws of physics, and with the billions of years of unique evolutionary history that have made our own world habitable. The universe does not readily yield to our desires. It presents a series of obstacles so profound that they force us to question the very feasibility of our grandest cosmic aspirations, pushing the boundaries of what is possible and what may forever remain in the realm of dreams. The red dust of Mars and the distant, cold light of the stars serve as constant reminders of this immense, almost impossible challenge. The human element body, mind, and spirit in the void. Our very consciousness, that ephemeral yet profound phenomenon that allows us to gaze at the stars and contemplate our place among them, to formulate these grand dreams of cosmic expansion, is itself a product of exquisite biological fragility. It exists because of the precise and delicate arrangement of approximately 86 billion neurons in our brains, interconnected by trillions of synapses, all operating within a tightly controlled biochemical environment. This remarkable organ, comprising only about 2% of our body weight, consumes a disproportionate 20% of our body's oxygen and glucose, maintained at an exact temperature and pH balance. Disrupt this delicate equilibrium for mere minutes through lack of oxygen, a significant change in temperature, or a chemical imbalance, and the intricate dance of neural activity falters, higher cognitive functions cease, and the light of consciousness, as we experience it, dims and then extinguishes. This same hypersensitive consciousness, so dependent on terrestrial stability, is what we propose to send into environments that actively seek to undermine its very foundations. The long-term physiological decay experienced in space is relentless, a slow-motion dismantling of our Earth-evolved bodies, beyond the immediate challenges of bone demineralization, muscle atrophy, fluid shifts, and radiation exposure. There are more subtle, cumulative effects that we are only beginning to understand. The immune system appears to be dysregulated in space, with some functions suppressed and others overactive, potentially increasing vulnerability to infections or autoimmune responses. The microbiome, the complex ecosystem of trillions of bacteria, viruses, and fungi that live in and on our bodies and play crucial roles in digestion, immunity, and even mental health, is likely altered by the confined, sterile environments of spacecraft, the specialized diet, and the physiological stresses of spaceflight. The long-term consequences of these microbial shifts are largely unknown. Cognitive function itself may be impacted by long-duration space travel. While the heroic image of the sharp-focused astronaut persists, studies have hinted at potential subtle declines in certain cognitive domains. possibly due to a combination of factors including radiation effects on the brain, chronic stress, sleep disruption, altered cerebral blood flow, and the monotonous, confined environment. The very structure of the brain can change, with evidence of fluid shifts within the skull and alterations in white and gray matter observed in astronauts after extended missions. However, the assault on the human element is not solely physical. The psychological toll of long-duration space missions, particularly for future colonists who may face lifetimes of isolation and confinement, is a profound concern. Humans are social creatures, evolved in open spaces, under blue skies, surrounded by the rich sensory tapestry of a living, breathing planet, the scent of rain, the feel of wind, the sounds of nature, the vibrant colors of a forest or a sunset. What happens to the human psyche when confined for years or even generations within the sterile, metallic corridors of a spacecraft or a Martian habitat, where every square foot is meticulously engineered and maintained at tremendous cost, where there are no natural horizons, no unpredictable weather, no spontaneous displays of natural beauty beyond the porthole view of a distant Earth or an alien landscape? Studies of individuals in isolated and confined environments on Earth, Antarctic research stations, submarine crews, long-term prisoners, reveal a spectrum of psychological challenges: depression, anxiety, irritability, interpersonal conflicts, sleep disturbances, and cognitive decline, often referred to as the third quarter phenomenon, where morale dips significantly partway through a long mission. These terrestrial analogs, however, occur under Earth's familiar gravity, with the knowledge that the natural world, friends, and family are ultimately reachable. For space colonists on Mars, millions of miles from Earth, the isolation would be far more profound, the confinement more absolute, and the possibility of return, if it exists at all, would be a distant and complex undertaking. The psychological weight of knowing that your survival and that of your community depends entirely on the flawless functioning of complex human-made technology, with no natural safety net, would be immense and unrelenting. Yet, amidst these challenges, there is also the potential for profound, even transformative, human experiences. Many astronauts who have viewed Earth from orbit or the Moon have reported a cognitive shift in awareness known as the overview effect. Seeing our planet as a fragile, luminous blue marble, suspended in the vast darkness of space, with no visible borders or divisions, often instills a deep sense of the interconnectedness of all life, a profound appreciation for Earth's beauty and preciousness, and a renewed commitment to its stewardship. It is an experience that can transcend intellectual understanding, becoming a deeply emotional and spiritual realization. Could this perspective, writ large across a future spacefaring civilization, foster a greater sense of global unity and responsibility? But as we contemplate adapting to survive in these alien realms, we inevitably encounter deep ethical questions about adapting humanity itself. If the unyielding harshness of space demands more than our current biology can withstand, do we turn to genetic engineering to enhance radiation resistance, to modify our metabolism for different atmospheric compositions, or to reshape our physiology for different gravity wells? If we design artificial organs that function more efficiently in microgravity, or neural interfaces to augment cognitive function or mitigate psychological stress? At what point do these modifications begin to alter what it means to be human? Is such a transformation the ultimate expression of our adaptability, our ingenuity, our drive to survive and transcend limitations? Or is it a betrayal of our evolutionary heritage, a departure from the very nature that defines us, who decides what constitutes an acceptable alteration, and what are the potential unforeseen consequences of tinkering with the complex? interconnected systems of human biology that have been refined over millions of years. The children born on Mars or in orbital habitats would know no other reality. Earth, for them, would be a story, a legend, a distant blue point of light in their sky. Their senses would be attuned to the engineered environment, their bodies perhaps subtly different, shaped by reduced gravity and a different sensory input. Would they feel a connection to Earth? Or would their primary loyalty be to their new off-world home? Would they still consider themselves human in the same way terrestrial humans do? Or would they represent the first generation of a new, post-Earth branch of humanity? The first true aliens of our own lineage. These are not merely speculative flights of fancy. They are fundamental questions that will confront us if we seriously pursue the dream of becoming a multi-planet species. The human element, in all its complexity, body, mind, and spirit, is both our greatest asset and our most vulnerable component in the quest to live beyond Earth. The void challenges not just our technology, but our very identity, forcing us to ask what we are willing to become in order to survive among the stars. The unseen universe and its silent questions. The cosmic stage upon which we aspire to enact our grand dramas of exploration and colonization is itself a realm of profound mystery, far stranger and more enigmatic than our everyday intuitions can readily grasp. Our comfortable narratives about the universe's origins and structure often mask deep uncertainties and unsettling paradoxes. Consider the Big Bang, that common shorthand for the universe's genesis. The term itself, coined somewhat derisively, conjures an image of a colossal explosion occurring at a single point in a pre-existing void. But the reality, as understood by modern cosmology, is far more nuanced and mind-bending. There was no sound, for there was no medium to carry it. More fundamentally, the Big Bang did not happen at a specific location in space. Rather, it happened everywhere, simultaneously. It was an expansion of space itself, not an explosion in space. In the earliest moments, the entire observable universe, with all its nascent matter and energy, was compressed into an unimaginably hot, dense state. Space itself was unfurling, like an infinite flower blooming from an infinitesimal seed. If the universe has no edge, as current observations suggest, then asking where the Big Bang occurred is akin to asking where on the surface of an expanding balloon its inflation began. The expansion is happening at every point on the surface. This understanding, however, leads to its own set of puzzles. One of the most significant is the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, an omnipresent whisper of microwaves filling all of space, we observe an astonishing uniformity in its temperature across the entire sky. Regions of the CMB that are on opposite sides of our observable universe, so far apart that light, traveling since the dawn of time, could not possibly have crossed the distance between them, nonetheless share almost precisely the same temperature, down to tiny fractions of a degree. How could these causally disconnected regions have reached thermal equilibrium if they never had a chance to interact, to exchange heat? It's like finding 2 cups of coffee, brewed in separate, sealed rooms miles apart, having cooled to exactly the same temperature without any communication. To resolve this and other cosmological conundrums, the theory of cosmic inflation was proposed. This theory posits that in the first fleeting fraction of a second after the Big Bang, a period almost unimaginably short, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds, the universe underwent a period of exponential superluminal expansion. It didn't break the cosmic speed limit by having matter travel faster than light through space, but rather by stretching the very fabric of space-time itself at an accelerated rate. During this inflationary epoch, a region smaller than a proton could have expanded to the size of a grapefruit almost instantaneously. This rapid stretching would have smoothed out any initial temperature variations, explaining the uniformity of the CMB, and also flattened the geometry of space to the near-perfect flatness we observe today. But inflation, while solving some problems, introduces new questions and even more astonishing possibilities. What triggered inflation? What caused it to stop so precisely, allowing for the more leisurely expansion that followed, which permitted stars and galaxies to form? And if inflation happened once, could it be a continuous process, happening in other regions of a much larger reality beyond our observable horizon? This leads to the concept of eternal inflation and the multiverse hypothesis, the idea that our entire observable universe might be just one bubble or pocket universe among an infinite or vastly numerous ensemble of other universes, each potentially born from its own inflationary event, and each perhaps with its own unique set of physical laws, fundamental constants, and even dimensionality. If this is true, then what we call the immutable laws of nature might be mere local ordinances, provincial rules that apply only within our specific cosmic neighborhood. Imagine the implications for future interstellar explorers. Reaching the edge of our bubble could mean encountering a boundary where our physics gives way to something utterly alien, rendering our technology useless and our very biology incoherent. The strangeness of the cosmic stage extends to its most fundamental constituents. We believe we understand matter, the solid stuff of tables, chairs, planets, and our own bodies. But delve into the quantum realm, and this familiar solidity dissolves. Atoms, once thought to be indivisible building blocks, were revealed to be mostly empty space. A hydrogen atom, for instance, is about 99.999996% void. If its nucleus were the size of a pea, its electron would orbit roughly a kilometer away. You, solid as you seem, are predominantly empty space, a fleeting configuration of quantum fields, a ghost made of mathematical patterns held together by forces we can describe with incredible precision, but whose ultimate nature remains elusive. And these fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, present their own cosmic puzzle. Why these four forces? Why do they possess their specific, measured strengths? The universe appears to be exquisitely fine-tuned for complexity and the emergence of life. If you were to alter the gravitational constant by even a tiny fraction, stars either could not form or would burn out too quickly. Adjust the strength of the strong nuclear force slightly, and the elements necessary for life, like carbon, could not be synthesized in stellar furnaces, or atomic nuclei would be unstable. Tweak the electromagnetic force, and the very chemistry upon which life depends would break down. This apparent fine-tuning is often referred to as the anthropic principle, the observation that the universe's fundamental constants and initial conditions seem to be precisely those required for conscious observers like ourselves to exist and observe it. Does this imply cosmic luck of an extraordinary degree? Are we living in a specially selected universe from a vast multiverse ensemble where most other bubble universes remain sterile and lifeless because their physical constants are not conducive to complexity? Or is there some deeper, yet undiscovered, physical principle at work that necessitates these specific values? The cosmic inventory grows curiouser still when we consider the dominant components of the universe: dark matter and dark energy. All the ordinary matter we can see and interact with, the stars, galaxies, planets, and ourselves, accounts for only about 5% of the total mass energy content of the universe. Approximately 27% is attributed to dark matter, an invisible substance that does not emit, absorb, or reflect light, interacting with ordinary matter only through gravity. Its presence is inferred from its gravitational effects on the rotation of galaxies and the bending of light from distant objects. Dark matter forms the invisible scaffolding around which galaxies coalesce and cosmic structures form, yet we do not know what it is made of. The remaining 68% of the universe is even more mysterious dark energy. This is a hypothetical form of energy that permeates all of space and appears to be driving the accelerating expansion of the universe, pushing galaxies apart at an ever-increasing rate. Its nature is one of the biggest unsolved mysteries in physics. Think about that nearly 95% of our universe consists of substances and energies we cannot directly see, cannot touch, and barely understand. We are like explorers in the 16th century trying to map the globe with only 5% of its surface visible, navigating by the subtle effects of invisible currents and unknown landmasses. And it is into this vast, largely unknown ocean that we dream of launching our fragile colonial vessels. Amidst this cosmic grandeur and profound mystery, one observation stands out with unsettling clarity: the Great Silence. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Many, if not most, of these stars are likely to host planetary systems. Current estimates suggest there could be tens of billions of potentially habitable, Earth-sized planets in our galaxy. Given the age of the universe and the billions of years that many of these planets have existed under relatively stable conditions, it seems statistically probable that life should have arisen elsewhere, and that at least some of that life should have evolved intelligence and developed technological civilizations. Even if the emergence of such civilizations is exceedingly rare, say 1 in a billion suitable planets, there should still be thousands, if not tens of thousands, of spacefaring civilizations in our galaxy alone. Some of these would likely be far older and more advanced than our own. Yet, when we scan the skies with our radio telescopes, when we look for signs of astroengineering or interstellar travel, we find nothing. No unambiguous signals, no Dyson spheres, no evidence of galactic colonization. The galaxy appears hauntingly empty of the technological signatures we might expect. This is the Fermi paradox. Where is everybody? The silence is profound and deeply unsettling. Does it mean that life itself is incredibly rare? Or that the transition to intelligence is a major bottleneck? Perhaps technological civilizations invariably self-destruct before they can achieve interstellar travel. Or maybe the challenges of living beyond one's home planet, the very challenges we are contemplating, are so immense that they represent an insurmountable great filter that silences countless emerging civilizations before they can announce their presence to the cosmos. Or a more solitary thought. Perhaps we are truly among the first, or even the only, technological species to emerge in our galactic neighborhood. The unseen universe, with its hidden constituents, its mind-bending origins, and its deafening silence, poses not just scientific questions, but deep existential ones, casting a long shadow of uncertainty over humanity's ambitious dreams of cosmic expansion. The indifferent stage in humanity's uncertain future. The universe, for all its breathtaking beauty and intricate laws, operates with a profound and chilling indifference to the aspirations, struggles, and very existence of conscious beings like ourselves. There is no inherent morality woven into the fabric of space-time, no cosmic justice ensuring the triumph of good over evil, and certainly no special concern for the survival or extinction of Homo sapiens. Stars explode as supernovae, sterilizing any nearby planetary systems with lethal radiation, not out of malice, but because their core chemistry dictates it. Asteroids and comets, remnants from the solar system's formation, drift through space on gravitational tides, occasionally impacting planets and potentially ending billions of years of evolutionary progress in a geological instant, as one likely did for the dinosaurs. Gamma-ray bursts, the most powerful explosion in the universe, can erupt from distant galaxies, sending focused beams of high-energy radiation across intergalactic space, capable of stripping atmospheres and causing mass extinctions on any unprotected worlds in their path. These are not targeted assaults, they are merely the impersonal workings of cosmic mechanics. In this indifferent cosmos, any human presence beyond Earth would exist solely because we, through immense effort and continuous technological intervention, create and meticulously maintain the conditions for it. There is no natural, welcoming niche for humans anywhere but Earth. Every off-world habitat, every lunar base, every Martian colony, every generation starship would be a fragile, artificial island of habitability in a vast, encompassing ocean of lethality. Survival would depend entirely on the flawless, perpetual functioning of life support systems, radiation shielding, atmospheric containment, and resource recycling. This creates a fundamental contradiction at the heart of the space colonization dream we seek to expand human presence into a cosmos that is inherently hostile to that presence. We attempt to create persistence in an environment characterized by impermanence and entropy. We strive for safety and stability in a universe defined by cataclysmic violence and unpredictable danger. The challenge of replicating Earth's complex, self-regulating ecological systems, which took those 4.5 billion years to evolve their intricate web of interdependencies. Within the confines of an artificial habitat is perhaps the most daunting technological hurdle of all. Consider Earth's biosphere. It's not just a collection of organisms, but a dynamic system of interlocking cycles: the carbon cycle, the nitrogen cycle, the water cycle, the oxygen cycle, the rock cycle, all operating on planetary scales and over geological timescales to maintain a relatively stable environment conducive to complex life. The oxygen we breathe is not a permanent feature of our atmosphere. It is actively produced and maintained primarily by photosynthetic life, from rainforests to phytoplankton in the oceans. Without this continuous biological activity, atmospheric oxygen would gradually deplete as it reacted with minerals on the Earth's surface. To sustain human life in a closed habitat on Mars or in deep space, this entire planetary-scale life support machinery must be replicated, miniaturized, and managed with near-perfect efficiency and reliability. Every breath of air, every drop of water, every calorie of food, and every waste product must be meticulously accounted for, processed, recycled, and reintegrated into the system. The margin for error would be vanishingly small. A significant failure in the air revitalization system, the water reclamation process, or the food production units could lead to catastrophic consequences within hours or days. Earth's biosphere possesses enormous redundancy and resilience. If one ecosystem is damaged, others can often compensate. If one species goes extinct, others may evolve to fill its ecological niche. This robustness is the product of billions of years of evolutionary trial and error. Space habitats, by contrast, would likely be far less resilient, designed from first principles with a limited number of species and carefully engineered pathways, the most ambitious attempt to create a large-scale and materially closed ecological system on Earth. Biosphere 2 in Arizona during the early 1990s serves as a stark cautionary tale. Despite significant funding and scientific expertise, the 2-year experiment encountered numerous problems, Oxygen levels dropped to dangerously low concentrations. Many of the introduced pollinating insects died off. Most vertebrate species went extinct. Crop yields were insufficient to feed the 8 human inhabitants, and the crew themselves experienced interpersonal conflicts and factionalism. And this occurred on Earth, with access to external resources, sunlight unattenuated by vast distances, and the planet's natural gravity and magnetic field. Replicating such a system with even greater reliability for indefinite periods, millions of miles from Earth, is a challenge of an entirely different magnitude. The perpetual reliance on fallible, human-made technology for every aspect of survival would create an immense and unceasing psychological burden for colonists. They would live with a constant awareness that their existence hangs by the thinnest of technological threads, that a critical system failure, a micrometeoroid puncture, or even a human error could spell swift annihilation. This is a stark contrast to life on Earth, where even if our technologies fail, the underlying environment generally remains habitable, offering a natural safety net. In space, there is no such fallback. Technological regression that might cause hardship or societal decline on Earth would mean certain extinction for an off-world colony. Furthermore, the tyranny of distance, as discussed earlier, would have profound long-term consequences for the human species if we were to successfully establish multiple isolated colonies. Communication delays measured in minutes, hours, or even years for interstellar settlements would make real-time interaction impossible. This would inevitably lead to cultural divergence. Different colonies, facing unique environmental challenges and developing under conditions of extreme isolation, would likely evolve distinct languages, social structures, values, and even mythologies. Over many generations, subjected to different gravitational fields, radiation levels, and perhaps even deliberate genetic modifications, biological divergence could also occur, potentially leading to the splintering of Homo sapiens into new distinct species, no longer able to interbreed or perhaps even to fully understand one another. Is this cosmic diaspora the grand destiny of intelligence, to diversify and fill every available niche? Or does it represent a tragic fragmentation, a loss of shared human identity? The universe, in its cosmic indifference, sets the stage but offers no script. It provides the raw materials, the elements forged in stars, but no guarantees of success or even survival. Is our relentless drive to expand beyond Earth, to push against these seemingly insurmountable obstacles, a testament to a uniquely human capacity for transcendence, an expression of our deepest exploratory instincts? Or is it a form of collective hubris, a refusal to accept our inherent biological limitations and our profound dependence on our home planet? Perhaps it is a mixture of both. The history of life on Earth is a history of adaptation, of overcoming environmental challenges, of radiating into new niches. The transition from aquatic to terrestrial life was an epochal leap, fraught with peril for the pioneering organisms. Is the transition from planetary to interplanetary, and eventually interstellar, existence simply the next great evolutionary hurdle? As we stand at this crossroads, a species capable of dreaming of the stars but not yet truly capable of inhabiting them sustainably, we must confront these deep contradictions. The impossible challenge of living beyond Earth forces us to question not just our technological prowess, but the very essence of what it means to be human. What values do we prioritize? What aspects of our terrestrial heritage are essential to carry forward into the void? And what might we need to leave behind or transform in order to survive the long-term fate of Earth itself? And our Sun adds another layer to this existential calculus. Our planet will not remain habitable forever. In about 1 billion years, the gradually brightening sun will likely make Earth too hot for complex life. In about 5 billion years, the sun will exhaust its core hydrogen fuel and expand into a red giant, potentially engulfing the inner planets, including our own. On the longest of cosmic timescales, even the universe itself has a finite lifespan of productive activity, with star formation eventually ceasing and matter itself perhaps decaying into a cold, dark, empty expanse. Against this backdrop of ultimate cosmic transience, the drive to spread life and consciousness beyond our single, vulnerable world takes on a different, perhaps more urgent, meaning. If consciousness is a rare and precious phenomenon in the universe, then perhaps ensuring its long-term survival, beyond the lifespan of a single planet or star, is a moral imperative, a responsibility we owe not just to ourselves, but to the cosmos itself. The stars watch in silent indifference, their light traversing eons to reach our eyes. They have witnessed the rise and fall of countless worlds, countless possibilities. Our future among them remains unwritten, a narrative we are only just beginning to compose, fraught with peril, yet gleaming with the audacious hope that defines our species. The impossible challenge awaits, and with it, the potential for a transformation far more profound than simply changing our address in the cosmos. It is a challenge to redefine our place in the universe and, in doing so, to discover what humanity might yet become. The journey to the stars, as we have seen, is not a simple extension of our terrestrial adventures. It is a confrontation with the deepest truths of our existence, our profound biological connection to Earth, the staggering scale and indifference of the cosmos, and the inherent fragility of life and consciousness. The universe presents us with a fundamental paradox. It is the crucible that forged us, yet it is also an environment that actively seeks to unmake us the moment we step beyond our planetary cradle. Every law of physics, every biological imperative, every psychological reality seems to underscore the immense, perhaps insurmountable, difficulty of truly making a home beyond Earth. Yet, in the face of these overwhelming challenges, humanity continues to dream, to design, to reach outward. Is this mere folly, a species-level hubris refusing to acknowledge its limits? Or is it something more profound, an intrinsic characteristic of consciousness itself, to question, to explore, to strive to transcend its apparent boundaries? Perhaps our destiny is not to find easy answers or comfortable new homes, but to engage with these impossible questions, to push against the very fabric of what seems possible. In doing so, we learn more about the universe, but more importantly, we learn more about ourselves. The silence of the cosmos, the vast distances, the lethal environments, these are not just obstacles, they are mirrors reflecting our own vulnerabilities, our courage, our ingenuity, and our deepest fears. The attempt to live beyond Earth, whether it ultimately succeeds on a grand scale or remains a series of heroic but limited forays, will inevitably change us. It forces us to consider what aspects of humanity are truly essential, what we must carry with us to the stars, and what we might be willing to transform or even sacrifice. The stars will continue their silent vigil, indifferent to our triumphs or failures. Earth will continue its cosmic journey, a tiny oasis of life in an ocean of desolation. But the questions raised by our celestial ambitions will linger in the human spirit. What is our purpose in this vast, unfeeling universe? Are we merely a fleeting biological accident on a minor planet? Or are we the means by which the cosmos becomes aware of itself, a conduit for consciousness to spread, and perhaps, in some distant future, to comprehend the totality of its own existence? The path ahead is shrouded in uncertainty. There are no guarantees. But the human story has always been one of facing the unknown, of stepping into the darkness armed with little more than curiosity, determination, and the audacious hope that beyond the horizon lies something worth discovering. The impossible challenge of living beyond Earth may be the ultimate expression of this enduring human spirit, a testament to our refusal to simply accept the world as it is, and our unyielding desire to imagine and strive for what it might yet become. The cosmos waits. And we, children of Earth, stand at the edge, looking out. There are few moments in science when we sense, viscerally, that we may be on the verge of something extraordinary. Moments when the vast, silent canvas of the cosmos, for a brief instant, seems to speak. And now, just maybe, it has. In a small patch of sky, far from the glare of our own sun, orbiting a dim and ancient red star, there lies a world not like our own. It is heavier, larger, stranger. It is bathed in the ruddy glow of a star that will outlive us all. And yet, this planet, known only by the designation K2-18b, may be whispering to us across the interstellar dark. It may be whispering the signature of life, not a message, not a civilization, not yet, but something more primal, a molecule, a breath, a pattern in the spectrum of starlight that, if confirmed, could represent the first evidence that we are not alone in the universe. To some, it may sound unremarkable. After all, we've long believed that life must exist beyond Earth. The numbers alone are overwhelming, hundreds of billions of stars in our galaxy, each with the potential for planets. Life, we suspect, is not a miracle of Earth, but a probability of nature. But belief is not knowledge. Hope is not evidence. And so, we wait. We build our telescopes. We peer deeper into the cosmic dark, not to satisfy curiosity alone, but to find truth. And now, through the lens of the James Webb Space Telescope, we may have come closer than ever before. It began with water. In 2019, scientists using the aging yet still powerful Hubble Space Telescope observed water vapor in the atmosphere of K2-18b, a world more than twice the radius of Earth, orbiting in the habitable zone of its star, and now possibly hosting water. It was tantalizing, but not conclusive. Water alone is not life. Venus has water vapor in its clouds, and Mars once had rivers. Yet neither teems with the kind of vibrant biosphere we see here on Earth. Still, the signs were promising. Then, in 2023, Webb turned its gaze to the planet. With infrared vision far superior to any observatory before it, it analyzed the starlight that filtered through the planet's atmosphere during transit when K2-18b passed in front of its host star. And what it found sent ripples through the scientific community. Not just water, but methane, carbon dioxide, and perhaps, just perhaps, dimethyl sulfide. Here on Earth, dimethyl sulfide is produced almost exclusively by life. It is the molecule you smell near the sea, a byproduct of phytoplankton, the tiny organisms that form the base of the marine food chain. It is not a chemical easily formed by volcanic processes or photochemistry. If it truly exists on K2-18b, it may represent something profound, a biosignature. A sign that, in the vastness of space, biology has emerged a second time. Let us pause for a moment and consider what that would mean. For centuries, we have speculated about life elsewhere. It has inspired our fiction, our philosophy, even our fears. But never, until now, have we had something like this, tangible, measurable, scientific. If life has begun on K2-18b, then it has begun twice in the universe, once on Earth, and once 124 light-years away. And if it can begin twice, it may be everywhere. That realization alone would transform our understanding of biology. It would tell us that life is not an accident, but a feature of the universe. That the same laws of chemistry and physics that govern the stars and galaxies also give rise to molecules that replicate, evolve, and eventually wonder. but we are not there yet. Science demands caution. The detection of dimethyl sulfide is still tentative. A 3 sigma signal, meaning there's a 0.3% chance it's a statistical fluke. Significant, but not definitive. To claim the discovery of life, we will need more data, more observations, perhaps years of study. And yet, we are close, so close. In this documentary, we will explore the full story of K2-18b, how it was discovered, what we know of its nature, and what makes it such a compelling candidate for extraterrestrial life. We'll dive into the chemistry, the physics, and the astrobiology of this world, and we'll ask a question that has haunted science for decades. This planet, KD2-18b, may not give us that answer, but it might offer the first clue. And from there, everything changes. Because if we can detect one, we can detect many. If biology is out there, it will not remain hidden for long. We are no longer just observers of the stars. We are listeners, interpreters, seekers of meaning in molecules. And the next great revelation may not come from within our own minds, but from the light of an alien world. K2-18b, an ocean world hidden in starlight. It is a strange truth of our time that we are now more familiar with the atmospheres of planets light years away than with the depths of our own oceans. But perhaps it is not so strange. The universe beckons in ways that the Earth does not. It reveals its secrets to those with patience and light, and above all, to those who know how to listen. K2-18b is one of those secrets. It is a planet that orbits a star known simply as K2-18, a small red dwarf located 124 light-years from Earth in the constellation Leo. It does not shine brightly in our skies. You could not see it with the naked eye, and yet it has become the focus of intense scrutiny, not because of what it is, but because of what it might hold. Let us consider the fundamentals. K2-18b is what astronomers classify as a sub-Neptune. It is roughly 2.6 times the radius of Earth, and 8.6 times as massive. If we could stand upon it, and we probably couldn't, its surface gravity would be nearly twice that of Earth. A human body would feel heavy, burdened, as though the planet itself were trying to keep you close. But we likely would not stand on it at all, because K2-18b is almost certainly not a rocky planet. It is enveloped in a thick atmosphere, rich in hydrogen and helium. And beneath that atmosphere, if the models are correct, lies a vast global ocean. This class of exoplanet is still theoretical. We call them Hycean worlds, planets with deep oceans of liquid water beneath hydrogen-rich skies. They are unlike anything in our solar system. Not gas giants like Neptune, not rocky worlds like Earth, but something in between, a hybrid of atmosphere and ocean. Heat and chemistry, wrapped around a planetary core we cannot see. For decades, scientists imagined that life elsewhere would require a planet like ours, solid surface, moderate temperatures, thin atmosphere, but our observations have forced us to reconsider. Hycean worlds may be far more common than Earth-like ones, and they may, in many ways, be better suited for life, particularly microbial life that thrives in aquatic environments. On Earth, the first life emerged in water, perhaps in shallow pools heated by volcanic springs, or perhaps in the cold darkness of the ocean floor, near hydrothermal vents. These environments were protected, chemically rich, and persistent. Could the same be true for worlds like K2-18b? Let us examine its star. K2-18 is a red dwarf, the most common type of star in the galaxy, smaller and cooler than our Sun. Red dwarfs burn their hydrogen slowly, with lifespans measured not in billions, but in trillions of years. They are cosmic elders, destined to outlast even the last white dwarfs in the distant future. K2-18b orbits its star every 33 Earth days, placing it squarely within the habitable zone, the region where temperatures may allow for liquid water to exist on a planet's surface, or beneath its clouds. But red dwarfs are a mixed blessing. Because their habitable zones are so close to the star, planets within them often become tidally locked, with one side perpetually facing the star and the other cast in eternal night. They are also vulnerable to stellar flares, bursts of radiation that can strip away atmospheres and sterilize planetary surfaces. Yet there is hope. Recent studies suggest that some red dwarfs, like K2-18, may flare less frequently, and a thick hydrogen atmosphere could protect the oceans below from radiation. If such a world is indeed covered in water, then even a tidally locked configuration might still allow life. Circulation of heat through atmospheric winds or ocean currents could keep the planet temperate and stable. It is difficult to imagine what such a place would look like. If you could descend through the atmosphere of K2-18b, the light would grow dim and red. The sky would not be blue, but a murky, copper hue. Clouds would gather thickly, laden with vapor, refracting starlight into strange patterns. And below, perhaps, an ocean, an endless sea without continents or islands, no shore to stand on, no mountains to climb, just liquid depths and chemical complexity. In that alien sea, shielded from the harshness of space by kilometers of atmosphere and hydrogen gas, life might begin, not as complex animals or thinking minds, but as single-celled organisms, microbes, plankton-like entities that drift, metabolize, reproduce. In other words, the kind of life that gave birth to all others. Of course, we cannot see that ocean directly, not yet. What we have, instead, is spectroscopy, a science of inference. When K2-18b transits its star, a small fraction of starlight passes through its atmosphere before reaching our telescopes. Certain molecules absorb certain wavelengths of light, creating a fingerprint, a set of absorption lines that tell us what gases are present. That is how we know about the water vapor, the methane, the carbon dioxide, and perhaps, most intriguingly, the dimethyl sulfide. None of these molecules alone prove that life exists on K2-18b. They can all be produced by non-biological processes, volcanism, photochemistry, reactions between rock and gas. But together, in the specific ratios observed, they are suggestive. On Earth, this combination is found almost exclusively in marine biospheres, in ecosystems driven by microbial life. It is not a discovery, but it is a possibility, one that grows stronger with every observation and every new piece of data. K2-18b has become, in many ways, our first real candidate for an inhabited world, not a mirror of Earth, but something more ancient, more elemental, a planet of oceans and molecules, chemistry and time, and perhaps, if we are fortunate, a planet where life has taken root in the darkness beneath the clouds. What would that mean? It would mean that life is not the rare consequence of planetary coincidence, but the natural product of planetary chemistry. It would mean that the universe does not just allow for life, it encourages it. And it would mean that we are not alone, not even close. What the molecules are telling us. No song sung beneath the stars, no whispered declarations drifting between the galaxies. And yet, the universe speaks. It speaks through light, through the long, patient journey of photons across millions of years. It speaks in patterns, in the gentle sway of gravity, the symmetry of atoms, the geometry of orbits, and sometimes it speaks in the language of molecules. On a world like K2-18b, we cannot yet see oceans or clouds or distant shores. We cannot send spacecraft to skim its atmosphere or dive beneath its waves. But we can catch a few rays of starlight, filtered through its sky, stretched and shifted by its chemistry. From this light, we read its story. When the James Webb Space Telescope observed K2-18b in 2023, it did so not by imaging its surface, but by observing a transit when the planet passed in front of its host star, blocking a tiny fraction of its light. As this light passed through the planet's atmosphere, certain wavelengths were absorbed by gases, while others were allowed to pass. The result was a spectral fingerprint, a barcode of sorts, etched in infrared. It was this fingerprint that first confirmed what Hubble had already suggested: water vapor in the atmosphere of K2-18b. Not ice, not liquid, but vapor suspended in its upper atmosphere, possibly condensing into clouds. This was important. But it was only the beginning. Alongside the water, JWST detected methane and carbon dioxide, both carbon-bearing molecules, both vital in the story of life on Earth. And then came a surprise. The data contained hints, faint but persistent, of dimethyl sulfide, or DMS. Let us begin with the more familiar molecules, methane and carbon dioxide. Methane, on Earth, is produced in two main ways. It can arise abiotically through geological processes like serpentinization, where water interacts with certain types of rock under high pressure and heat. It can also come from biological activity, from microbes in wetlands, from the digestion of animals, from the decomposition of organic matter. Carbon dioxide is similar. It is a byproduct of combustion, of respiration, of volcanic activity. It is both a lifeline and a danger, essential for warming Earth but catastrophic in excess. The presence of both CH4 and CO2 on K2-18b in itself does not confirm life, but the ratio of these gases is curious. On Earth, their relative abundances are tightly linked to biological cycles. Methane is quickly destroyed in our atmosphere by sunlight and chemical reactions. If it is present in significant quantities, it must be constantly replenished. The same appears to be true on K2-18b, which raises the question, what is maintaining the balance? Is it chemistry? Is it geology? Or is it biology? Now we come to dimethyl sulfide, the molecule that has caused such a stir in the astrobiology community. On Earth, DMS is not just produced by life. It is, as far as we know, produced only by life. More specifically, it is released by marine phytoplankton, microscopic organisms that inhabit the sunlit layers of our oceans. As they die and break down, they release dimethylsulfonopropionate, which is then converted into DMS. It rises into the air, influencing cloud formation and even the planet's climate. It gives the sea its smell. And if the detection on K2-18b is real, and that is a significant if, it would suggest not just chemistry, but biology, a biosphere, a living ocean. But how confident can we be? The detection of DMS was made using JWST's mid-infrared instrument, MIRI. It was independent from the earlier measurements made by its NIRS-SPEC and NIRIS instruments. That's important. It means the signal didn't come from noise in a single channel, or an artifact of a specific instrument. Statistically, the detection sits at 3 sigma. That means there is a 99.7% chance the signal is real, and a 0.3% chance it is a fluke. In physics and astronomy, we typically require a 5 sigma detection, corresponding to a 1 in 3.5 million chance of being wrong, before claiming a discovery. The team behind the DMS claim has requested more time with JWST to confirm their result. If granted, and if the signal holds, it will likely become the strongest biosignature candidate in the history of observational astronomy. Still, caution is warranted. There are non-biological pathways for methane and carbon dioxide. DMS is harder to explain, but not impossible. It could be a byproduct of some exotic photochemistry in hydrogen-rich atmospheres, perhaps a process we have not yet seen on Earth, or not under the conditions of K2-18b. Astrobiology, by its nature, walks a fine line between evidence and enthusiasm. We want to believe, but belief must wait for confirmation, and so the debate begins. Could this be a new class of chemical system? A prebiotic chemistry producing DMS analogs? Could it be a fluke? A data reduction artifact? A misidentification? To strengthen the case, researchers turn to models. They simulate K2-18b's atmosphere under different assumptions: volcanic outgassing, photochemical equilibrium, hydrothermal vents, and again, the models suggest that abiotic sources struggle to produce the observed concentrations of these gases together, especially DMS. Moreover, the concentrations are high, significantly higher than what we see on Earth. That's surprising, but not necessarily problematic. In fact, some theoretical work had predicted exactly this outcome for Hycean worlds with life. A thick hydrogen atmosphere traps heat and slows chemical reactions, Gases that would quickly dissipate on Earth could linger far longer. And in an ocean world without continents or seasonal turnover, microbial life could dominate the biosphere almost entirely, leading to a planet-scale bloom of organic chemistry. In short, the fingerprint matches. It is not proof, but it is not coincidence either. There is, of course, one more tantalizing possibility. If K2-18b is not an ocean world, but a small gas dwarf with no surface, then the presence of DMS becomes far more difficult to explain by natural processes. There would be no ocean in which microbes could thrive, no seafloor, no hydrothermal vents, just gas. In that case, the detection would no longer be a biosignature. It would be something else entirely. It would be a technosignature, a sign not of biology, but of technology, of intelligent life releasing complex molecules into its atmosphere. There is no reason to believe that is the case, but it cannot be dismissed out of hand, because once you eliminate the biological and the geological, what remains? And so, we are left here, suspended between hope and hypothesis, between signal and noise. The molecules are whispering. They may be speaking of biology, or chemistry, or something we have never seen before. If K2-18b holds life, it will reveal itself not with trumpets and declarations, but with molecules drifting silently in the light of a red star. All we need to do is continue to watch. Could life thrive there? To ask whether life exists on K2-18b is to ask more than whether molecules can survive there. We are not merely seeking chemistry. We are seeking biology. Not atoms, but cells, not reactions, but replication. And that is a far deeper question. Because life, once begun, is persistent. It adapts, it evolves. But to begin, to truly take hold, it needs more than the right molecules. It needs an environment that can sustain it, protect it, nourish it, let it grow. Could K2-18b be such a place? Let us imagine, not from the stars above, but from the sea below. Beneath its thick hydrogen-rich atmosphere, K2-18b may conceal a vast global ocean, perhaps hundreds of kilometers deep. Unlike Earth's oceans, it would have no continents, no islands, no shallows, no shores on which to crawl and evolve limbs, just water, deep, dark, and endless. At the top, the ocean would be blanketed by an atmosphere rich in vapor, perhaps turbulent with clouds. But as you descend, the light would vanish, filtered by kilometers of water. The pressure would rise to unimaginable levels. And somewhere far below, there might be a rocky core, a silent surface warmed by the slow release of radioactive heat and tidal forces. It is here, in this profound darkness, that life might begin. On Earth, life may have originated in just such a place. Hydrothermal vents, deep beneath our oceans, are cracks in the seafloor where heat and minerals pour into the surrounding water. Around them, entire ecosystems thrive, ecosystems that do not rely on sunlight, but on chemistry, on chemosynthesis, on the conversion of chemical energy into biological order. Tube worms, giant clams, and swarms of microbes form colonies around these vents, bathed not in light, but in sulfur. If K2-18b has such vents, they could be cradles of alien life. Even in the absence of a rocky surface, there may be floating layers of water ice or supercritical fluids that allow for chemical gradients, gradients that drive metabolism, that allow molecules to store and release energy, the fundamental requirement of life. The ingredients may be there. The processes may be there. The question is, can life, once sparked, thrive? Let us consider the challenges. The most obvious is gravity. K2-18b is significantly more massive than Earth, which means its surface gravity could be nearly twice as strong. On land, that would make life difficult. Walking, flying, even circulation of fluids within organisms would be more taxing. But in water, gravity's effects are softened. Buoyancy helps. Organisms float, drift, swim. The ocean becomes a protective womb. Indeed, the earliest life on Earth remained in water for billions of years. Complex, multicellular organisms evolved under the surface long before the first fish ever contemplated the land. So perhaps gravity would not be an obstacle, at least for microbes and other soft-bodied creatures. On Earth, sunlight powers the biosphere. Photosynthesis turns light into sugar. But if K2-18b is a Hycean world, its oceans may be so deep and its clouds so thick that sunlight never penetrates far. Photosynthesis, at least as we know it, may be impossible. But again, Earth shows us a way forward. In the deep sea, life thrives without sunlight. Chemosynthetic organisms use hydrogen sulfide, methane, and other compounds as energy sources. Similar processes could exist on K2-18b, where abundant hydrogen and carbon-based molecules offer potential fuel for alien metabolism. Perhaps, in the darkness beneath its clouds, entire ecosystems have evolved based not on light, but on chemistry. Still, one must ask, could life evolve intelligence in such a place? This is a more delicate matter. Intelligence, at least in the form we understand it, arises from complexity, from ecological interactions, long-term memory, communication, and environmental pressure. Life in a featureless, endless ocean may lack many of these drivers. Without land, there are no tools, no fire, no metallurgy. Even building a shelter becomes difficult. How does one smelt metal in a deep ocean? How does one harness electricity? In short, even if life thrives, it may remain simple, and that may be the answer to one of the deepest mysteries in all of science, the Fermi paradox. The paradox asks, if the universe is teeming with habitable planets, perhaps even with life, then where is everyone? Why do we not see evidence of advanced civilizations? No spacecraft, no signals, no ruins on the moon, no great Dyson spheres harvesting starlight. Just silence. Perhaps the answer is this, but intelligence is rare. And not because evolution doesn't favor it, but because most life is born in worlds like K2-18b. Worlds with oceans but no land, with pressure but no fire, with chemistry but no tools. Civilizations may never arrive, not because they fail, but because they never had the chance. The universe may be filled with biospheres, but almost devoid of technospheres, a sobering thought, but also a hopeful one. It means we might find it elsewhere, on Europa, on Enceladus, beneath the ice of exomoons and dwarf planets. It means that we are no longer wondering if we are alone, but how many neighbors we have yet to meet. And perhaps, one day, we will not only observe them, but help them. Imagine a distant future in which humanity becomes the uplifter, the bridge between worlds locked in their oceans and the cosmos that waits beyond. We, born of a planet with both ocean and land, might be the rare creatures who escape, who travel, who share, who listen not just for voices, but for life itself, in whatever form it may take.
In the year 2020, we have images of black holes, breathtaking panoramas of the Milky Way, detailed snapshots of distant galaxies, and the stunning James Webb Telescope is getting ready for launch. However, 30 to 35 years ago, everything was so different that such news would likely have shocked engineers and scientists. If we had the opportunity to call a scientist directly in the year 1985 and ask a couple of interesting questions, like the existence of planets around other stars, they would probably say that it's likely, but not certain. Now, it's not 1985 anymore, and thanks to new methods and modern technology, today we have thousands of stars in our own galaxy that have their own solar systems. We have discovered planets of various sizes, characteristics, and masses at various distances from their stars. We have planets even larger than Jupiter that orbit stars in less than 48 hours, and NASA's Kepler mission has made a huge contribution to the search for such planets. It's no longer breaking news that Earth-like planets are being discovered. But let's reason more simply. As each of us has a specific idea of what intelligent life is, and each of us has an idea of the conditions under which this life can exist. Let's imagine a simple analogy: intelligent life in the universe and an ordinary tree. If I ask you whether a tree can grow inside an iron box, or whether it can exist there, you would accurately say no, because you understand that a tree requires certain ingredients, such as soil, fresh air, sunlight, and some nutrients. In fact, the logic is such that we just need to find the same things that exist on Earth, and then we will surely find life. This is how we think now. But consider the fact that you are not Mickey, defining the concept of life only like the one on our Earth, because you haven't seen any other life, heard nothing about it, and are unlikely to hear about it in the near future, and maybe never. So, if we set ourselves the question of searching or pondering whether intelligent life exists in the universe, it's important to understand correctly what form or type of life we want to find. It could be similar to us or something entirely different. Of course, the simplest ways to answer such a question are to apply mathematics, probability theory, and real observations. But in that case, once again, we will be looking for life solely similar to ours. Remember that tree I mentioned? The key point is that we know what it looks like and what conditions it needs. Therefore, we can easily predict where a tree can grow and where it's extremely impossible. If you want a simple answer to the question of whether life exists somewhere in the universe besides us, I will say that it's 100% likely, given what we consider as life. I know this is my personal opinion, but I will try to explain why I'm confident about it. I present to you 10 amazing places in the universe with a full potential for the formation of life. It's not a secret that soon after the formation of our planet, life appeared on Earth and is progressing today. Of course, it's possible that earthly life didn't originate on Earth, but came from somewhere else through natural cosmic processes. And in this conversation, it doesn't matter whether it originated here or somewhere else. What's important is that the basic ingredients for life exist everywhere we look. For example, consider a dozen places where these ingredients are most frequently found. First, there's gas ejected from young objects, like the Herbig-Haro objects, which contain various organic molecules. Another example is protoplanetary disks, where there's a vast diversity of complex compounds and organic molecules. For instance, there's the protoplanetary disk around the young star, H.L. Tauri, photographed by ALMA. The gap in the disk indicates the presence of new planets, and spectroscopic measurements reveal a large variety of carbon-containing compounds, which are essential for life. Even on Pluto, there's thallium and methane, and a rich organic haze. Even in the images from the New Horizons mission, atmospheric hazes are clearly visible and measured for the content of several carbon-containing compounds. Nebulae illuminated by a bright young star are rich in numerous complex carbon compounds, are reflective nebulae for containing a wide variety of complex organic molecules. Reflective nebulae are common sources of raw materials for life. By the way, inside meteorites, there are numerous amino acids and proteins, some of which are not found in nature on Earth. For example, the Murchison meteorite that fell in Australia in the 20th century. The fact that there are more than 80 unique types of amino acids suggests that basic ingredients for life, or even life itself, could have formed differently somewhere else in the universe, perhaps even on a planet that is not orbiting a sun-like star. The gas in the galactic center includes vital compounds. Idol's Pharma is responsible for the recognizable aroma of raspberries, though Russian scientists don't acknowledge this. For example, the wave image of the galactic center shows us stars and gas, with a tremendous amount of material, including heavy elements and organic compounds, which are essential precursors for life. And this is the molecular cloud of Taurus, where new stars are formed. It contains dozens of organic substances, including carbon chains. For example, in the image, the brighter areas in red have the highest density and active star formation, while the blue areas correspond to cooler, less dense regions. However, organic molecules are found in both places. Planetary nebulae formed by the death of sun-like stars contain more than 20 molecular species, including fullerenes. These are abundant on Earth. Interestingly, fullerenes and complex organic compounds can form rapidly and survive to a significant extent during the evolution of any star. Nitrogen, hydrogen, and oxygen are strongly highlighted in this planetary nebula. Different colors clearly indicate the locations of various elements, which are separated from each other. Complex molecules, including fullerenes containing 60 carbon atoms each, have been detected in these planetary nebulae. And you don't have to go far. Sedimentary rocks on Mars contain rich organic compounds, some of which are over 3 billion years old. For example, the American NASA rover on Mars discovered ancient organic molecules embedded in sedimentary rock deposits that have existed for billions of years. They contain carbon and sulfur and could be associated with life beyond Earth. Over the past decades, our knowledge of the existence of planets around other stars has grown to incredible numbers. The number of known exoplanets has changed from a few dozen to more than 1,000 officially confirmed objects. Therefore, now we are confident that exoplanets can come in various sizes, be at different distances around all types of stars, have different masses and characteristics, and these are real data. It's not surprising that against the backdrop of such acquired knowledge, various questions arise in our minds, seemingly logical at first glance. For instance, when will we find the first inhabited planet beyond the solar system? Or what does habitability on a planet actually mean? Do planets exist that closely resemble our home, Earth? All this is done in order to understand where else life might exist. However, the thing is, the more we learn, the more we realize that being interested in and searching for a planet similar to ours with the presence of life is very inappropriate. This is because the universe is incredibly diverse, and places with the presence of life might not be anything like Earth. Perhaps these conditions could be even better or completely different from what we can imagine. We'll talk about why the assumption that a planet similar to Earth is a requirement for the existence of life is misleading. Having only one successful example, the planet we inhabit, leads to this kind of misconception. If we look at our solar system with all its planets and moons surrounding us, it becomes obvious that Earth is something unique. Only we know why we consider it special. Maybe it's because Earth is the known world where life originated, was sustained, developed, and flourished. It transformed the biosphere and eventually became complex, diverse, intelligent, and technologically advanced. Scientists are looking for conditions that resemble those Earth has experienced and continues to experience. They assume that a potentially habitable planet with life must be similar to Earth. But this is where they make a crucial mistake, because these assumptions imply that the conditions our Earth has faced are the most favorable for the desired outcome of life. However, as we learn more about the universe and the solar system, we have solid grounds to challenge such an assumption. There are 5 key points we need to consider. The first thing that comes to mind is a planet the size of Earth. After all, it seems like the ideal size for life. If we're too large, we might be enveloped in a massive hydrogen or helium envelope, like Neptune or Uranus. And if we're too small, we might struggle to maintain our atmosphere, like Mars or Mercury. Hence, the conclusion is that Earth's size is the way to life, right? Saturn's moon Titan is smaller than Mars, yet it maintains a denser atmosphere than even Earth. Moons like Europa, a large watery moon of Jupiter, might have ideal conditions for subaquatic oceanic life. Isn't it paradoxical and intriguing? These typical examples are right here in our very own solar system, yet they don't remind us that the potential for life exists in many worlds of vastly different sizes. The size of Earth is not a special prerequisite for life to form. The second point worth mentioning is the so-called habitable zone. If we have a planet the size of Earth with an atmosphere, we need to place it in a favorable location around its parent star to have the necessary temperature for life to initiate. This also seems logical. However, the thing is, a planet much farther from its star can have a denser atmosphere, leading to moderate conditions. A planet with a lower albedo or specific cloud cover properties might be closer to its parent star and still have moderate conditions. Hot planets could thrive in their upper atmospheric layers, while cooler planets could harbor life beneath ice. The habitable zone is a fifth-place starting point, and science has progressed to a point where this simplistic definition is no longer useful. The third point is the ability of a sun-like star. The majority of stars in the universe are red dwarfs, low-mass stars that burn slowly and steadily, in contrast to only about 20% of stars that share the fate of the sun, burning for billions of years before becoming red giants and ending as planetary nebulae. Although red dwarfs mostly have a low mass and undergo very slow nuclear reactions, emitting little light, many planets orbiting them are locked by tidal forces. However, this doesn't mean these conditions impede the formation of life. There is a risk of cutting off unnecessary possibilities by limiting ourselves to our primary assumption. While it's more likely that life in red dwarf systems may be challenging, until we truly start conducting a census of the universe's population, measuring the atmospheric properties of all available planets, we cannot make a comprehensive conclusion that life in these systems doesn't exist at all. The fourth point is that life regulates its own biosphere. This is another key question for which we don't have an exhaustive answer. Can a planet, initially uninhabited and considering only physical and chemical processes, transform and remain habitable during the early stages of simple life? We know Earth has many feedback mechanisms, and we also know that significant external changes might result in only minor changes within our biosphere. Does having simple, early forms of life hold the key to the development of stable, long-lasting life on a planet? After all, the conditions for its origin are more realistic and favorable. If this is the case, we cannot significantly understand what makes a planet potentially suitable for life until we gain a more complete understanding of this matter. The fifth point is the significance of heavy elements. The very first generation of stars consisted mostly of hydrogen and helium. In our solar system, about 2% of the total mass of all objects consists of heavier elements such as oxygen, carbon, nitrogen, and other essential life elements. Stars with a sufficient amount of heavy elements cannot form rocky planets, nor the simple molecules necessary for life. However, where do we draw this line? Can a solar system made up of half heavy elements be sufficient for life to form? And what if the percentage is 10, or even just 1? Or perhaps it could be as high as 500% in the opposite direction. Therefore, regardless of a specific threshold, we lack a clear understanding of whether we are a rarity in the universe or a typical outcome of probability theory. These are just some of the open questions that hinder our comprehension of a planet similar to Earth. An intriguing fact is that the universe plays with numbers. Consider our observations, for example, within the Milky Way. There are approximately 10 billion Earth-sized planets orbiting within the habitable zone of stars similar to our Sun in terms of temperature and mass. A significant portion of different systems have a comparable concentration of heavy elements to our solar system, indicating that a vast number of exoplanets could potentially be candidates for Earth-like conditions. However, there are also numerous exoplanets of a different type that do not meet these criteria. Such planets are far more abundant than those we naively describe as being similar to our own. The quest for Earth-like planets may lead us to overlook many planets in the galaxy where life may have already originated and begun to thrive. In order to discover something, a more unbiased approach would be to observe everything within our capability. Of course, it's easy to argue that Earth possesses all the conditions for life, which should at least allow us to consider the possibility that planets with similar conditions could also harbor life. So let's start by acknowledging the imperfections in our search for life on exoplanets. It's this kind of thinking that ensures we will obtain biased results in any search we conduct. But if, before the search even begins, we simply decide that life cannot exist around red dwarfs, that exoplanets or moons of incorrect sizes or at incorrect distances from their stars will never form life, or that stars with insufficient heavy elements cannot support life-bearing planets, we risk not only overlooking numerous cases of life in the universe, but also the overwhelming majority of habitable planets. The thing is, nearly 80% of the stars in the galaxy are low-mass stars, and there may well be more worlds the size of Mars or Liverpool, smaller than Earth, orbiting these stars than Earth-sized worlds. There's probably a multitude of atmospheric conditions that can permit life at various orbital distances. There might even be more exomoons of significant size around gas-rich massive exoplanets than Earth-sized exoplanets. So how tempting it is to assume that if we have one successful example like Earth, we should seek examples that mimic that known success. However, this is an incorrect scientific approach, the correct approach is to seek as many plausible worlds as possible that could include these conditions, not limiting ourselves to only Earth-like conditions. It's entirely possible that most planets with conditions similar to Earth's are actually inhospitable to life. Meanwhile, many planets with conditions different from ours may be even more suitable for life. Until precise studies reveal the answer, presuming that Earth 2.0 has a precise scientific basis is speculative at best. The story of how the universe became what we see today, from the Big Bang to the vast space filled with galaxies, stars, planets, and life, unites us all. From the perspective of inhabitants of planet Earth, 2/3 of cosmic history passed before the appearance of the Sun and Earth. However, life emerged on our world as far back as we can peer into the past through measurements. It may have appeared even 4.4 billion years ago. This makes us wonder, did life arise in the universe earlier than on our planet? How long ago might it have emerged? To be more precise, how soon after the Big Bang could enough heavy elements accumulate to form planets and possibly life? The answer to this question takes us further into the past than we could ever imagine. Graphite deposits have been discovered in zirconium, which is the oldest evidence of carbon-based life on Earth. The amount of carbon-12 found in these deposits dates the emergence of life on Earth to over 4 billion years ago. Of course, we cannot travel back to the very beginning of the universe, because after the Big Bang, there were not only no stars or galaxies, there were not even any atoms. Everything takes time to come into existence, and the universe, after giving birth to matter and antimatter, started from a fairly homogeneous state. The densest regions comprised only a small fraction, possibly as small as 0.3%, denser than the average. This means it would take an enormous amount of time for gravitational collapse to work on creating, for example, planets that are much denser than the average density of the universe. Yet, the universe had enough time for all of this to come into existence. If we look at the standard timeline of the universe's history, Earth appeared only after 9.2 billion years after the Big Bang, but many of the steps necessary for creating a world like ours happened very early on, just after 1 second. Antimatter annihilated with the majority of matter, leaving a small amount of protons, neutrons, and electrons. A sea of neutrinos formed, and after about 3 to 4 minutes, protons and neutrons combined to form neutral atomic nuclei, but most of these were isotopes of hydrogen and helium. Only when the universe cooled down to a certain temperature, which took approximately 380,000 years, did electrons join these nuclei, forming neutral atoms. However, even with these fundamental ingredients, life and rocky planets were still impossible because cooling the universe meant that atomic nuclei formed, followed by neutral atoms. Yet, practically all of these atoms were hydrogen and helium. Only much later did the heavy elements necessary for the formation of rocky planets and life begin to form. But gravitational collapse is a reality. Given enough time, it will change the face of the universe. At first, it progresses very slowly, but it gains momentum as regions of space become denser. The denser the region becomes, the better it is at attracting more and more matter, and the areas that start with the highest density grow faster than others. Our simulations show that the very first stars should have formed approximately 50 to 100 years after the Big Bang. These stars should have consisted solely of hydrogen and helium and could grow to quite large masses, hundreds or even thousands of times the mass of the Sun. When such a massive star forms, it dies within 1 to 2 million years, but in the moment of its death, something remarkable happens, all thanks to its life. All stars synthesize helium from hydrogen in their cores, but the most massive ones not only synthesize carbon from helium, they also progress to oxygen, neon, magnesium, silicon, sulfur, and so on, following the periodic table of elements until they reach iron, nickel, and cobalt. After this, there's nowhere else to go, and the core collapses. This triggers a supernova explosion. These explosions eject a vast amount of heavy elements into the universe, giving rise to new generations of stars and enriching the interstellar space. The increase in the proportion of heavy elements signifies an increase in the number of rocky planets with high density and the quantity of elements necessary for life as we know it. We don't need the average stellar system in the universe to resemble our solar system. We only need a few generations of stars to live and die in the densest regions of space to replicate conditions suitable for the emergence of rocky planets and organic molecules. For instance, in the remnants of a supernova, there exists a slowly rotating neutron star, formerly a massive star that reached the end of its life. Although supernovae can send the synthesized heavy elements back into the universe, it's the subsequent mergers of neutron stars that create most of the heaviest elements. By the time the universe reaches just 1 billion years old, the most distant objects are abundant in heavy elements, as confirmed by our measurements. There is a significant amount of carbon, as much as in our solar system, and other heavy elements accumulate even faster than carbon. It may take more time to achieve a high concentration because carbon primarily emerges in stars that do not become supernovae themselves. However, carbon is not essential for rocky planets, and other heavy elements also start to accumulate more rapidly. Possibly within several 100 million years after the ignition of the first stars, around 300 to 500 million years after the Big Bang, the most enriched stars have already formed rocky planets. This is seen in the protoplanetary disks around young stars. Gaps in these disks indicate the presence of new planets. As soon as the disk has a sufficient amount of heavy elements, rocky planets can emerge within it. If carbon were not essential for life, similar processes could begin in different regions of the cosmos. However, for life similar to ours, carbon is crucial, which means that the appearance of life may need to wait much longer. Even though carbon atoms will appear in the mix, it will take approximately 1.5 billion years for there to be enough of it. This period is before the universe reaches 10% of its current age. However, it's not just the 5% required for the formation of rocky planets. It's interesting to consider that the universe has formed planets and all necessary ingredients in the right quantities for life to emerge, except for carbon. To create a sufficient amount of this essential ingredient for life, we must wait until the most massive sun-like stars live and die. You see the remnants of supernovae on the left and a planetary nebula on the right. Both of these mechanisms allow stars to return burnt heavy elements to interstellar space, utilizing them for the emergence of stars and planets in the next generation. Sun-like stars, after their death, leave behind planetary nebulae, which are the primary source of carbon in the universe. It takes more time for the production of carbon because stars that give rise to planetary nebulae have longer lifespans than those that perish in supernova. Extrapolating that back into the past, the most advanced forms of life that appeared on Earth in different epochs suggest an interesting exercise. It turns out that the increase in genome complexity follows a certain trend. If we go back to individual paired bases, the time frame suggests something more like 9 to 10 billion years, rather than the 12 to 13 billion years ago the Earth formed. This indicates that life could have emerged a billion years ago. However, in our cosmic region, it took several additional billion years to initiate. On this semi-logarithmic graph, the complexity of organisms, measured by the length of non-redundant DNA relative to the functionally non-redundant DNA, with respect to gene readability through paired nucleotides, linearly increases over time. We do not know this at the current moment. We do not know where the line between life and non-life is drawn. We also do not know if earthly life began here before other formed planets, or somewhere deep in interstellar space without any planets at all. Many amino acids not found in nature have been discovered in the Murchison meteorite, which fell to Earth in Australia in 1969. The fact that over 80 unique types of amino acids exist in a simple cosmic rock suggests that the ingredients for life, or even life itself, might have emerged through interactions on planets. It's intriguing, the elementary ingredients necessary for life appeared shortly after the formation of the first stars, and the most important ingredient is carbon. As the fourth most abundant element in the universe, carbon is the last ingredient to reach the necessary quantity for rocky planets. In some places, rocky planets appeared much earlier than life could have emerged, perhaps as soon as 500 million years after the Big Bang, or even earlier. However, once we have enough carbon, all the necessary steps for the emergence of organic molecules and the initiation of the direction towards life become inevitable. Whatever life processes led to the emergence of humanity, they might have begun when the universe was 10 times smaller than it is now. We can be certain that in our solar system, we are alone. The maximum possibility is the existence of some microbes. These would not be complex multicellular organisms. But where are the intelligent beings? If intelligent beings truly exist in the universe, their location is at least light years away from us. Two independent intelligent civilizations could coexist, excluding interstellar travel. If they followed a similar path as our life, the question arises, where are they? Perhaps we should start with the fact that to emerge, life must go through several stages, yet the ingredients for it are literally everywhere. Even if we limit ourselves to life chemically similar to ours, the universe is teeming with possibilities. Molecules capable of binding, including organic ones, are present both on planets and in space. This is the Omega Nebula, or the Messier 17 mission, an intensely active star-forming region, which explains its dusty and vivid appearance. Stars formed at different stages of cosmic evolution have different proportions of heavy elements. Although Earth formed over 9 billion years after the Big Bang, the universe didn't necessarily have to wait that long. Therefore, we'll categorize stars into 3 population types. The first population type includes sun-like stars, which consist of 1 to 2% heavier elements than hydrogen and helium. They are composed of processed material, and their planetary systems have gas giants and rocky planets suitable for life. The second population type consists of older, ancient stars with only 0.1% of the heavy elements found in the Sun. Most of their worlds are gaseous and rarefied. They are too primitive and contain too few heavy elements for life to emerge. The third population type includes the earliest stars in the universe, which should be almost entirely free of heavy elements. The study of the earliest galaxies indicates that they are mainly composed of stars from the second population type. However, closer to us, there is a mix of young and old stars, rich and poor in metals. In star distances, the scale is accurate in this illustration, but if the picture were to scale, even the largest stars would be smaller than 1/1,000,000th of a pixel. One of the most important lessons for astronomers came from the Kepler mission when examining the Kepler 4444 system. This first population-type star has planets, but they are much older than our Earth. Our planet is only 4.5 billion years old, while the Kepler 444 system is 11.2 billion years old. This means the universe could have formed Earth-like worlds very early, at least 7 billion years before Earth appeared. Considering this possibility and the fact that regions like the center of our galaxy got enriched with metals faster and more significantly than our surroundings, it's quite possible that there are places in the universe, maybe even in our Milky Way, more conducive to the emergence of intelligent life than the Sun-Earth system. Given all that we know about the positioning of stars well suited for the birth of life, such as how closely 2 different civilizations could be, and where we should search for them, the answer might change based on these conditions. Let's consider 5 main possibilities. This is the imagination of an artist regarding the TRAPPIST system, with its planets reflecting light from their surfaces. The potential presence of water on each of these worlds is depicted through seas, ponds, and vapor. However, it's unknown if any of these worlds have an atmosphere or if their parent star blew it away. One thing is clear. Potentially habitable worlds are located close to each other at a distance of only 1,000,000 kilometers. In the early days of the solar system, it's likely that Venus, Earth, and Mars, and perhaps even Theia, a hypothetical planet that collided with Earth, had conditions equally suitable for life. Their atmospheres were filled with life-building ingredients, and there was liquid water on their surfaces. Venus and Mars at distances close to Earth's mark, a trajectory that spanned tens of millions of kilometers. However, around a Class M star, a red dwarf, planets could be separated by distances much smaller, as seen in systems like TRAPPIST-1. Potential habitable worlds could be as close as 1,000,000 kilometers apart. Twin moons or planets orbiting a giant world or a binary planet could be even closer to each other. If life successfully emerged under certain conditions, why not have it arise twice, almost in the same place? This is a globular cluster, Omega Centauri, captured using a powerful telescope. Closer to the cluster center, you can see higher density, but the stability is comparable to any other region. Globular clusters are massive collections of hundreds of thousands of stars, forming a spherical shape with a diameter of a few tens of light years. In the outer edges, the typical star-to-star distance is about a light year, but in the denser inner regions of these star clusters, stars can be as close as the Sun and the Kuiper Belt. Orbits in these star systems must remain stable, even in such crowded surroundings. Considering what we know about globular clusters, which appeared much earlier than the Kepler 4444 system, there should be promising candidates for life and habitability within a few hundred astronomical units. Although this distance changes over time due to star motion, you could call this an incredibly close encounter of two civilizations. This high-resolution image operates very close to the infrared range. Such pictures allowed us to discover 3 superstar clusters in the galactic center. Since long-wave light near infrared penetrates the dense dust between Earth and the galactic center, we could observe these superstar clusters. This cluster is from the central parsec, and all stars in these clusters, as well as the galactic center, are quite young. The closer you get to the galactic center, the denser the stars are. In a few light years from the center, star density is extremely high, much greater than the center of a globular cluster. In a sense, the galactic center is an even denser environment with massive black holes and extremely massive stars and clusters forming. While globular clusters lack these, there is a problem with those stars in the sense that we see them in the Milky Way's core. They are relatively young, possibly due to high variability in their local environment. Stars rarely survive there for even 1 billion years, despite the high density. In this area, stars come in different sizes, colors, and masses, including many bright blue stars, which are dozens or even hundreds of times more massive than the Sun. This is evident in the scattered star cluster NGC 3766. So, let's consider the existence of a civilization in a densely packed star cluster, or a spiral arm. Spiral arms are rich in unusual regions of the galaxy, where young stars are more likely to form from these epochs. Star clusters often contain thousands of stars within a region just a few light years in size. However, stars don't remain in such a configuration for very long. A typical open star cluster disperses in just a few million years, and only a small fraction of them survive for billions of years. Stars constantly enter and exit spiral arms, including our Sun. In summary, while the typical distances between stars within a cluster may be around 1 light year, they are unlikely candidates as the cradle of life. This logarithmic diagram displays distances, showing the Voyager spacecraft, our solar system, and the nearest star. So, let's consider the latest idea that everything is distributed in interstellar space. In other cases, stars end up in the same situation we observe, distances between them being on the order of a few light years. Approaching the center of the galaxy, we can reduce this distance to what is encountered in open clusters, approximately 1 light year. But if we get too close, we face the problems we see in the galactic center: mergers, interactions, and other catastrophic events that are more likely to interfere. To maintain a stable environment, we can reduce the distance, but the typical interstellar space is not suitable for this. If we adjust for close encounters, the best approach would be to wait until another star passes close to the initial one. With a typical star, this happens approximately once every million years. This graph represents the probability of a star passing at a specific distance from the Sun, with both axes being logarithmic. While we don't expect intelligent extraterrestrial life to be a frequent phenomenon in the universe, as common as planets and stars, every world that meets the necessary conditions represents a chance. Each time you get a chance, you gain an opportunity for success, with a finite probability. Each of these possibilities may turn out to be reality, but until we venture there and see what is there and what isn't, it is essential to objectively assess what kind of extraterrestrial intelligence the universe may provide us. The truth is somewhere out there, but it's important to understand that if we were extremely lucky, it could be much closer than we dare to imagine today.